Good morning dear students, welcome back. I am a physics professor Dr. Nagaraj. So I am explaining right now statistical physics. Already I have uploaded 2 videos on this particular topic. So in the previous video I was talking about Poisson's distribution. I gave several examples for Poisson distribution and also the mathematical form of Poisson's distribution. It is nothing but a distribution function which explains the discrete distribution actions like accident happening in particular area in 1 year, or number of steps that you put in 1 kilometer distance, or number of disintegrations taking place in one given unit mass of gas, nuclear substance, or number of collisions happening within the container where gas molecules are moving randomly. All these things can be discussed with the help of Poisson's distribution. And Poisson's distribution, as I told in the previous video, gives the probability of the count. X is equal to k. K is a whole number. It is equal to lambda to the power of k e to the power of minus lambda divided by k factorial. You know all the details. K is nothing but a even number and non-negative, not a even number. It is a number, whole number, non-negative whole number. It can be odd also. Lambda, that is nothing but the happenings, counts in a particular interval of time. How many steps you put in 1 kilometer distance, or how many steps you put in 100-meter distance, or how many atoms undergo disintegration in 1 hour, or how many accidents happen in one day, or how many eggs are laid by the hen in 1 hour, how many collisions occur in 1 minute, like this. That is one particular event. Overall average, if you take, it is lambda. Lambda need not be a whole number, it can be even a fraction also. So all these things we have discussed in detail in the previous slide. Now let me take one particular application, that is modeling of proton decay. First I give you the background of proton decay. Please remember, proton decay, what I am explaining is the individual proton decay. In PUC you have already studied about beta decay. In beta decay there are 2 types, negative beta, positive beta. Negative beta is beta only, that is electron. Positive beta is positron. So negative beta means electron and positrons are produced when neutron converts into proton, proton converts into neutron. That is not actually decay. So here decay means individual proton independently converting into some other form. So okay, proton converts into pion and positron with a half-life of 10 to the power of 33 years. Just imagine how big this number is. According to theoretical calculations, an individual proton undergo disintegration with such a huge average time, lifetime, mean lifetime represented by tau. In PUC you have studied 2 lifetimes. One is half-life, another one is mean time. Half-life is the time interval during which the substance reduces to 50% of the previous one. Mean life is reciprocal of decay constant, is equal to 1 by lambda. Please dear students, don't get confused between this lambda and this lambda. They are totally different. For time being I write this as lambda radioactive. That is lambda coming in Poisson's relation, this is coming in radioactive equation. Another lifetime what you studied in PUC is T half, that is half-life. That is time interval during which the sample reduces to 50% of the initial amount. Okay, and also you have studied one famous equation, that is n is equal to n naught into e to the power of minus lambda t. This lambda is this lambda r. Okay, so that is radioactive decay constant. Got it? So theoretically, actually as of now we don't have any clue about the proton decay. Okay, if at all proton decays, it has to decay with a mean life of 10 to the power of 33 year. Just imagine, it is 1 followed by 33 zeros, right? Crores of years. But age of the universe, do you know? Age of the universe is about 14 billion, or roughly we can write 1.4 into 10 to the power of 10 year. Not age of the earth, it is age of the universe. That means compared to age of the universe, proton life is much greater than. Okay, so anyway, that is one thing. Now coming back to the actual topic, that is modeling of proton decay. So proton decay, according to theoretical calculations, converts into a pion and a positron. There are certain rules to be satisfied, certain conditions to be satisfied for any particle to undergo decay. For example, charge must be conserved, spin must be conserved, mass and energy must be conserved, and baryon number must be conserved. Like that, there are so many conditions to satisfy. Then only the decay will happen. Actually, in the case of proton decay, as of today, we have not noticed even a single decay at all. Right? If at all, if it happens, one decay will take 10 to the power of 33 years. Right? So that means to say, you have one proton in your hand. In order to check whether it converts into pion and positron, how many years you will have to wait? Not 1 year, not 2 year, not 1000 year, 10 to the power of 33 year. You have to wait. You have to look at that proton, whether it undergo decay or not. It is highly impossible. Right? Now let us try to understand this in more detail. Before that, let me come back to introduction part. Even this is also introduction only. Now I give a little bit of introduction to Poisson's distribution role in this particular case. See, certain rules and laws will forbid certain action to happen. For example, law of conservation of momentum, law of conservation of energy, like that. Almost all the laws of conservation laws will forbid certain action to happen. Law of conservation of energy says it is impossible to create energy or destroy energy. Okay, total energy is always conserved. Like that, even charge conservation also, total charge is conserved. So if you apply these laws, then definitely certain decay processes are forbidden, certain happenings are forbidden. Okay, so law is forbidding few things to happen, few decays to happen. This is theoretical prediction. Some people are trying to conduct experiments. They conduct experiments to check the validity of these laws, whether this law is really true or not. For example, if you can produce energy out of nothing just by doing like this and create energy, then it is you can easily say law of conservation of energy is not correct. But so far, you believe it or not, we don't have even a single example for violation of conservation of energy. Even though law of conservation of energy is not proved theoretically, not disproved experimentally, ivattina tanaka not even a single experiment we have seen where you can generate energy without anything. You can create energy but at the cost of something. So you cannot create something at the cost of nothing. So it is impossible. So energy conservation law na disprove madak agilla. If you want to check the law, you conduct some experiment. Your intention is to disprove the law, but finally you will end up with theory only. That means you cannot disprove the law. Similarly, decays. See, some theories forbid proton decay. Proton decay is not possible anta prove madidave kelu theories. Some conservation laws have already proven that proton decay is not possible. But still across the globe, all over the world, experiments are going on to check, is there any minute possibility, thin possibility, faint possibility to see the proton decay. So such type of experiments are called null experiments. Null experiments are conducted not to discourage law. Please remember, it is not to discourage the law, not to disprove the law, just to strengthen the law. By conducting null experiment, by getting the result which is equal to the theoretical prediction, it is actually going to boost up the law. So it increases the confidence level of the law. So null experiments intention is mainly to improve the confidence level of the conservation laws. This is the background. So even in beta decay also such type of experiments are conducted, and in these experiments Poisson's distribution law is used. See, in Poisson's distribution law we use all possible theories, all possible happenings, all possible values, and we do calculations. Correct? No? For example, here my intention is to see whether proton is undergoing decay or not, either in 1 year or 2 year or 3 year or 10 year. I want to see. Okay, please recall the egg example. Hens, in one day 20 hens keep 20 eggs, but in first 1 hour duration, how many eggs are laid? 0 eggs are laid, K is 0. 10 eggs are laid, K is 10, like that. So I want to check how many protons are undergoing decay. 0 protons undergo decay, so I write K equal to 0. 10 protons undergo decay, I write K is equal to 10, and then I do some calculations. That's what I am going to do immediately after this explanation. Finally, I get some answer. Suppose my answer is 1 or 2, probability, p-value, probability if it is 1 or 2 or 3, that means to say that there is a probability of proton decay. There is a probability of proton decay. That means the law is wrong. So that means I am disproving the law. If I don't get p is equal to 1 or 2, if I get p is equal to 0.05, 0.005, 0, something like that, that doesn't mean that law is 100% perfect. Law is not 100% perfect anta helangilla. Of course, law may be correct, but still I have speculation about the law. I have to increase the decay time or upper limit. I have to increase, that is the lifetime of this tau. Keep this sentence in mind. I will elaborate it at the end. So background decay I want to check, proton decay I want to check. With the help of distribution law, I will try. Okay, the distribution law, if comes out to be positive, like 1, 2, huge number, that means the law is disproven, decay is happening. If the probability comes out to be very, very, very less, then it doesn't mean that there is no proton decay. There may be proton decay, but may not be in 10 to the power of 33 years, maybe in some other higher upper limit of lifetime. Like that, I have to draw the conclusion. It is like this, for example. I have one person, say this is not a very good example, but I think it is going to convince you. I have one person over here, and somebody predicted that he is going to die today. Okay, I waited for 1 day, but he didn't die. Does it mean that he is not going to die forever? Okay, no, it is not like that. He may die, may not be today. His life span is more. That means he will live for few more years, maybe another 10 years or another 20 years, something like that. So this type of conclusion we have to arrive. Same thing applies even to the proton also. You are expecting the proton to die in 10 to the power of 33 years. If you don't get I am not waiting up to 10 to the power of 33 years. That is the beauty of distribution law. Poisson's distribution will not tell you wait for 10 power 33 years. You need not do. It is impossible to wait for 10 power 33 years. Okay, Poisson's distribution will give you some clue about the upper limit of the lifetime. Okay, I don't know whether this introduction he is convincing you or not. Let me now come back to the actual problem. Your actual problem starts now only. Well, this type of experiment, that is null experiment, has been taken up by one team in Japan, and that experiment name is Super K or SK experiment. Okay, let me write the full form. Super K experiment, and the experiment started in 1996. There they have taken a tank of 40 meter tall. Just look at the effort they have put. 40 meter tall, 130 feet radius cylinder chamber tank filled with 50,000 tons of water, pure, ultra pure water. Okay, and the whole arrangement is buried deep in the ground. This is the ground, earth, deep in the ground at a depth of 1 kilometer. The whole tank is buried in the ground so that there will be no interference of the atmosphere with the procedure or experimental setup. Okay, this is the brief background of Super K experiment taking place. Even today it is there and going on in Japan. 40 meter length tank with 130 feet radius filled with 50,000 tons of pure water buried in the ground at a depth of 1 kilometer. And according to the calculation, 50 into 10 to the power of 3 and the 50,000 tons of water consists of 7 into 10 to the power of 33 protons. You can do this calculation with the help of Avogadro number. So N0, at present there are 7 into 10 to the power of 33 protons. If at all proton undergo decay, then you have to use this equation. So that equation I write here. n is equal to n naught e to the power of minus lambda t. Anyway, lambda I already told you it is reciprocal of tau, okay, and lambda is therefore, I write it here, so tau is 10 power 33, therefore lambda r is 10 to the power of minus 33. So decay constant is very, very small. Therefore, we can write e to the power of minus lambda t. Of course, it is lambda r. I should not write lambda r. It is not a correct notation, just to avoid the confusion. ಯಾಕೆಂದ್ರೆ already ಅಲ್ಲೊಂದು lambda ಇದೆ. Okay, this can be written as it is exponential binomial expansion becomes 1 minus lambda t. Of course, it is lambda r. Therefore, this equation n is equal to n naught into 1 minus lambda r into t. Simplify further. This becomes n is equal to n naught minus n naught into lambda r into t. So simplify further. N naught minus n is equal to n naught lambda t, just after reshuffling the terms. Dear students, here n is number of protons available after t seconds, after t hours, after t decades or t years. In general, t is time, right? N naught is the initial number when the experiment started in the year 1996. Okay, n naught we know, n we know, t we know, lambda we know. Substitute and simplify. So this comes out to be, if I take t is equal to 1 year, this comes out to be n naught minus n is equal to, so if I take this t as 1 year, this comes out to be n naught is 7 into 10 to the power of 33 into lambda is 10 to the power of minus 33, t is 1, so I have n minus n, n naught minus n is equal to 7. What actually does it mean, you know? It means n naught is the initial number, n is a number after 1 year, so n naught minus n must be number of protons decayed in 1 year. This type of problems you have done in PUC. N naught, let us say 100, n is 90, that means 100 minus 90, that is equal to 10 atoms are disintegrated. So in total, n naught minus n represents number of atoms disintegrated in 1 year. Okay na? So in this tank there are so many, not this, these many protons. Out of 7 into 10 power 33, every 1 year 7 protons should undergo decay and they should convert into pion and positron. They should convert, if at all they undergo decay. Underline this word. ನಿಜವಾಗ್ಲೂ ಪ್ರೋಟಾನ್ ಡಿಕೆ ಆಗೋದೇ ನಿಜ ಆದರೆ ಒಂದು ವರ್ಷಕ್ಕೆ 7 ಪ್ರೋಟಾನ್ಗಳು ಡಿಕೆ ಆಗಬೇಕು, 7 ಪ್ರೋಟಾನ್ ಡಿಕೆ ಆಗಿ ಪಯಾನ್ಗಳು ಮತ್ತೆ ಪಾಸಿಟ್ರಾನ್ಗಳು ಹೊರಗಡೆ ಬರಬೇಕು. ಅರ್ಥ ಆಯ್ತಾ? ಸೇ ದಿಸ್ ಕಂಟೈನರ್ ಈಸ್ ಸರೌಂಡೆಡ್ ಬೈ 40% ಆಫ್ ದ ಡಿಟೆಕ್ಟರ್ಸ್. 40% ಡಿಟೆಕ್ಟರ್ಸ್ ಅನ್ನು ಇಟ್ಟಿದ್ದಾರೆ ಸುತ್ತಲೂ, ಆ ಕಡೆ ಈ ಕಡೆ ಎಲ್ಲ 40% of the chamber is covered by the detector, right? Suppose if you cover it by 100% detectors, your detector should read how many? It should read 7 counts, right? Since I have covered it only 40%, then my detector read 40% of 7, that is 2.8, approximately 3. That means, according to my detector, every 1 year 3 counts must be there. This is my lambda in the Poisson's formula, dear students. This is not the lambda which is decay constant. It is lambda in the Poisson's relation. Gottagta idya? So in the tank 50,000 tons of pure water is there. In that pure water 7 into 10 power 33 protons are there. If at all proton is decaying, every 1 year 7 protons should die and our counter must read 3. Got it? Sir, why you are taking so many protons? You can take only 1 proton. Yes, this is a problem. Actually, it's a good question. In fact, I told you in the beginning, if you have 1 proton in your hand, how many days you will have to wait? You have to wait for 10 power 33 years. 1 proton, 10 power 33 years. Okay. This decay is actually probabilistic. It is probabilistic. One proton may take 10 power 33 years. If I have huge number of protons, one or two of them may die immediately. It is like human normal lifespan. Normal lifespan of human beings is around 80 years, let us say. 80 years means in a locality there are 500 people. That doesn't mean that all 500 people live 80 years full. Okay, maybe unfortunately some people may die at the younger age itself. Okay, maybe at the age of 10 itself you need not have to wait 80 years to see all of them whether die or not. Actually, I should not talk about the death, but this is little bit convincing example, that's why I am taking. Please don't think in the other manner. Okay, so take it in a positive sense. ಈಗ ಯಾವುದೋ ಒಂದು ಏರಿಯಾದಲ್ಲಿ 500 ಮೆಂಬರ್ಸ್ ಇದ್ದಾರೆ, ಅವ್ರು ಎಲ್ಲರೂ 80 ಇಯರ್ಸ್ ಬದುಕ್ತಾರೆ ಅಂತ ನಾವು ನಾರ್ಮಲ್ ಆಗಿ ಹೇಳ್ತೀವಿ. ಅದರ ಅರ್ಥ ಆಲ್ 500 ಆರ್ ನಾಟ್ ಲಿವಿಂಗ್ 80 ಇಯರ್ಸ್. ಅದರಲ್ಲಿ ಯಾರೊಬ್ರು ಬೇಗ ತೀರೋಗ್ಬೋದು, ಮೇ ಬಿ 10 ಇಯರ್ಸ್ ಓನ್ಲಿ, ಮೇ ಬಿ 3 ಇಯರ್ಸ್, ಮೇ ಬಿ 7 ಇಯರ್ಸ್, ಮೇ ಬಿ 70 ಇಯರ್ಸ್ ಆಲ್ಸೋ. ಲೈಕ್ ದಟ್ ಇನ್ ಮೈ ಹ್ಯಾಂಡ್ ಐ ಹ್ಯಾವ್ ಸೋ ಮೆನಿ protons, right? So I need not have to wait up to 10 power 33 years. One of them may die, one of them may decay, one of them may disintegrate, if at all it is disintegrating. If at all it is disintegrating, it has to disintegrate in some possible time. Okay, that is the intention why we are going for such a huge number of protons. Okay, assuming that there is a decay, there will be 3 counts. Assuming that there is 3 counts. Now 1996 they started the experiment. Even today not even a single decay they have noticed. That means k equal to 0. K equal to 0, dear students. Now we have lambda, we have k. Substitute in that formula. P of k is equal to 0, or sorry, x is equal to 0 is equal to lambda, that is lambda, that is 3 to the power of k, this equation, to the power of k is 0, into e to the power of minus 3 divided by 0 factorial. Take calculator and simplify, you get this answer as 0.05. I told you, no, but I cannot arrive at that conclusion. I cannot say conservation law is right. I cannot say conservation law is right. I can only say, since probability is so small, the upper limit of this lifetime should not be 33, it must be more than 33. Beginning I gave you an example. If you say the person is dying today, if he don't die today, it means that he is not going to die tomorrow or day after tomorrow. His lifespan is not 10 year or not 1 year. He may live another 15 year or 20 year. Like that you have to increase the upper limit of the lifespan. Same thing in case of proton decay also, scientists have done. They have set the limit of lifetime not to 10 power 33 to 1.34 into 10 to the power 34 years. On what basis they have arrived at the conclusion is not required for us, but of course it is on the basis of some calculations only. Here what we have to see, proton decay is suggesting us to set the upper limit for the lifespan. Sir, okay sir, it is right, but basically tell me whether proton is undergoing decay or not. It is $1 million question. Even today nobody have found any satisfactory answer for this, but at the same time not even a single proton decay has been witnessed by any of the people across the globe, including America, including India. Experiments are going on to check the proton decay, but it so happened that not even single proton decay has been seen. Proton is immortal as of now. 10 power 34 years is very much greater than 10 power 10 age of the universe. Okay, so this is about modeling of proton decay. So overall summary, proton decay, if at all happening, there must be 7 counts per year. According to Poisson's, probability comes out to be 0.5. What probability? Getting no decay. 0 decay probability 0.5. This suggests that upper limit of the lifetime is not 10 power 33. It must be further increased, 1.34 to 10 power 34. This is the proton decay modeling. Okay, so I have explained everything. And one more thing, Poisson's distribution is actually not uniform distribution, but for larger values of lambda, I told you already in the previous video, for smaller distribution for smaller lambda it looks like this, for larger lambda it looks like this. This is normal distribution, where left distribution is equal to right distribution. In day-to-day life we see so many examples for normal distribution, like height of the people. Okay, we have small, average, large, and even that side also. And blood pressure, it keeps on changing, it is also normal distribution. Marks obtained by the students in your class, okay, you have 70, you have 60, you have all possible 50 if you take center, that side, this side, uniform distribution. All these are examples for normal distribution. For normal distribution, you get a curve called bell-shaped curve, and this peak of the curve gives you mean or median of the distribution. So dear students, all these details are available in my PDF. Please, link is given here, please follow. And in my next video, I will come back with the numericals on Poisson's distribution. Also, I am going to upload videos on numerical problems from different topics. Keep watching, like my videos, so that I also get the encouragement to do more and more videos. Of course, you are giving very good feedback. Simultaneously, keep the like button also. Keep pressing like button also. Thank you, dear students. Thank you very much.